Hi, Anthony. I finally got a chance to look over some of these problems that you handed me on Thursday night. So I looked into a few things, trying to get a few ideas online about what they were getting at and how to approach the problems. I don't think I have a full solution for either one of them for you, but I can give you some ideas to at least explore, I think, that will lead you in the right direction in terms of these. So the first question, they're talking about an infinite checkerboard, and it really doesn't matter because whatever's true for one square will be true for all of the squares, so it won't change the probability overall. And so from what I can gather, the way that we need to approach this is to think about this coin and to concentrate more on the fact, like on the center of the coin and where it's landing, because that lets us define an area where the center of the coin can land. And the reason that we do that is because we know the distance from the center to the outside edge of the circle, which is the radius. And we know the radius in this case, I think they said that it's exactly, the diameter is exactly half the length of the sides of the squares, they said, right? So let's choose a number example. Let's say that the square is 10. That would make the diameter of our coin, the diameter 5, which would make the radius equal to 2.5. So what we need to do is figure out the size of the square that the center of the coin can land in so that it stays inside the border of our checkerboard square. And so by that I mean that we need to stay at least 2.5 centimeters. The center of the coin has to be at least 2.5 centimeters away. And so if we are going to have a smaller square inside that's going to leave a border of 2.5 centimeters, that's the area of all the places where the center of our coin can fall. So the length then of that square is going to be 5 by 5 because we're taking 2.5 centimeters out of each side on the border here and here and here, right? So in our numerical example, the area of the smaller square, we'll call that square 1, is 5 times 5, which is 25 centimeters squared. The area of the larger square, which we'll call square 2, is 10 by 10, which is 100 centimeters squared. So the probability of our coin landing within the border that we've defined is 25 out of 100, or 1 in 4. Now, that on itself worries me a little bit, and that's why I don't have a final answer for you on this one, because if you allow that border to be exactly 2.5 centimeters, then I think you would actually be touching the outside edge of the bigger square. So how do you make it, just inside that? So the probability would have to be like of slightly less than 25 over 100 maybe. I'm not sure exactly how you would do that, but this would get you close, and this would at least allow you to answer the bigger question, which is this a fair game? If the coin touches the side of one or more of the squares, then your opponent keeps it, but if it lands inside and doesn't touch the edge, then you win because you get the coin and you get 3 more coins. So you get your coin back and you get 3 more coins. So because your winnings are 4 coins to 1, and the probability is 1 in 4, I think that makes this a fair game. So your winnings are you win 4 coins every time you bet 1, you get 4 coins back. So I think that makes this a fair game, but I'm going to refer you to the notes from your class where you've been talking about the odds and what a fair game entails, and use the definition that you've been given there to sort of phrase that and decide on how you're going to proceed in terms of your conclusion there. I think I'm going to make you a second video so that these videos aren't too long to talk about the second question. So I'm going to stop here and send you over the first video, and then I'll send you the second one later.